Okay, thanks. So today I'd like to talk about mesh-independent topology optimization done in FEniCSx. And apologies, it's not going to be a type of talk about the core of the Phoenix. It's more an application of the Phoenix. This is a joint work that I did at the company called FEniCSx with my colleague Johannes Neumann and Jack Hale from the University of Luxembourg. So what is FEniCSx and what do we do? It's a small startup type of company based in Luxembourg, Berlin, and London. And we essentially develop a cloud-based topology optimization software, which is called Mobius. It has a graphical user interface, as you can see at the bottom. And it allows stochastic optimization, so something that incorporates uncertainty in the load conditions, very useful in the practical application. It does adaptive anisotropic mesh refinement, a bunch of manufacturing constraints, very useful for industrial clients, stress constraints, and others. So here you can see a bunch of example shapes coming out of that application. It's of course all 3D. I mean, no 2D examples. I will only talk about 2D examples for the purpose of the talk. Here, this is the standard industrial benchmark. It's an Airbus aerospace hinge. Some hinges placed on the airplane, and some motor bracket. So, what is topology optimization for the minimum compliance? So, this is the standard problem setup, right? We are minimizing a compliance, functional C, and we are looking for displacement solution U, instance space U, and the placement of the material phi in the space V. Now we have a constraint such that the density has to be bound between 0 or something small and 1, and we have a bound on the volume, and then we have a bound such that the elasticity equation holds. So the very standard topology optimization for minimum compliance setup from 80s. Okay, you can equivalently formulate this as a Lagrange functional, right, where you put all the constraints together, and then we also use a standard SIMP penalization for the density dependence of the stiffness. Now, if you look at the literature, of course, you'll find out that the continuous problem does not have a minimum, right? It's not well posed, so you have to somehow regularize it. There are a bunch of methods proposed in the past. So you either add the local, global constraints on gradients, you add various type of penalties into your functional, or you introduce an ad hoc filtering approaches where instead of your density, you formulate it in terms of some smoothed density, introduces a length scale, or, and this is the one related to the work I did here, you introduce sensitivity filters. So essentially you compute the gradient of your functional, and then you apply some operator onto it, which introduces a length scale. So this is called the sensitivity filters in the engineering kind of topology optimization literature. Now, if you look at the literature, what you will find out is that the sensitivity of the functional, of that compliance functional, you will find a statement like this, that the sensitivity with respect to the L2 metric is given by some expression that depends on your solution, the state solution, and the adjoint solution, which is the same here because it's self-adjoint problem. And then you probably could run a gradient descent-based optimizer, and you would update the previous state with the sensitivity information. Now, this is, of course, in the L2 space, and what you have to do, you have to use a Riesz representation, because really your derivatives are functionals, right? The linear functionals. So for every derivative, I have represented in the space such that it acts with the scalar product. Now, this scalar product H is a scalar product on your space over which you're optimizing, and it's really an arbitrary inner product. In the traditional engineering literature, this is usually an L2, or rather a small L2 or capital R2. And what I'm going to show here is what is the effect of choosing a different inner product. This is also known in the shape optimization community as a Hilbertian framework, by mapping the shape derivatives using a Riesz representation theorem. So So you might look up the gradient descent in the Hilbert spaces. So this is just a small alteration there, right? The next state, the next density is going to be the previous one times the step size, and then you have a resmap of your gradient, and then you really have to compute the resmap of that sensitivity. Now, for a specific choice of H1 now being the scalar product, I did not do the H1 kappa because there is a length scale kappa, which is very important, right? Because you don't want to be adding things of different units together, which is in mathematical literature usually kappa is 1, but this is not correct. So this has a meaning of regularization, and it controls then the optimal solution that you find. So this will be demonstrated on a simple example. So then essentially what you do, you solve a very simple positive definite Helmholtz PDE to map to find the risk representer of the sensitivity. Oh, yeah. Whenever you see such an H1 norm that doesn't have a kappa, right, this is what keeps me awake at night. So here I'm going to look at that type of scalar product choice for a specific algorithm, the algorithm called optimality criteria. And it's essentially type of sequential approximate optimization, where what you do, you approximate your functional. You can also call it the quasi-Newton method, because you approximate the functional because you know how it behaves locally in terms of your density. So because it locally behaves as inverse of phi, what you could do, you can write some kind of approximation where it's equivalent to the second order expansion, where you choose a Hessian with a specific form. And what you could do in addition, you can play with all kind of quasi-Newton methods. You can choose a Hessian, which is implicit in the density. You can choose the one which is explicit in the density, and this is the specific method I chose here. So then you can take Hessian depending on the density from the previous iteration, and you have an extra parameter where you can choose essentially like a step size, how fast the algorithm, what type of minimum is the algorithm picking. And you have a traditional optimality criteria method in the black, and the different choices essentially of the gamma parameter in practice governs how fast you are removing material in areas where it's not needed, and how fast you're adding in the regions where the material is needed. This is something with a very nice practical interpretation. So if you revisit back the traditional results on the existence of optimizer for that formulation, you will see a bunch of requirements, right? So we needed that the set of admissible densities should be bounded in the space we're optimizing. The exponent p should be limited, which doesn't hold anyway, but okay. And then some requirements on the solvability on the forward equation. So because we don't have yet the bounded set of admissible densities, we have to add some regularization term into our reciprocal approximation, right? Now, what happens is that now your approximation to the functional is not a local equation, so you can't solve it at every quadrature point or whatever. Now you have a PD. So again, it's a nice type of PD because it's positive definite. So we can use a CG solver. I'll talk about it later. And this type of term is called W1P type of penalty, Tikhonov regularization, and whatnot. Okay, so in the nutshell, the algorithm looks like this. You solve the state equation, you solve the risk representer, and then you solve the optimality criteria equation. I didn't list it here explicitly. And then you have a volume constraint. Yeah, for this, for the small examples I will show you, I was using FEniCSx, and really the solver you see which solver you could be using which method, which is rather efficient in this case. So I have a 2D examples. What happens? So the standard cantilever, loaded on the right side. And this is what happens if I just increase that inner product scale, right? So I have a more regularization internally from the inner product, and I see that the smaller features are disappearing, and only the larger features are appearing. Also, the smallest curvature in the shape is limited. And this is without any regularization. So the Tikhonov regularization is 0. What you can find out, okay, this is a convergence. And this is what happens if you have a locally refined mesh. So what you see is really that the refined shape does not depend on the mesh refinement. This is okay. And this is without an extra regularization. So this is perfect. You almost see that the thickness of the member that goes across the mesh is not affected, right? However, if you look at the convergence, so you see this is converging into the same shape, but the number of iterations is growing, and this is an effect of absence of the regularization. So even though this is the standard sensitivity filtering method in the engineering community, what you have is that the shape to which you converge is the same. However, the limit is not in the H1 space. It's a piecewise discontinuous shape, and you're trying to approximate it by H1 CG1 functions, and that gives you the dependence of the number of iterations. So unless you study, there are not many studies like that for the number of iterations in the sensitivity filtering community. So unless you check that explicitly, you would not notice an exploding number of iterations. Now, what happens if I decrease the inner product length scale as the mesh is decreased? What I will see is that the number of iterations stays roughly the same or just a small growth. However, there are new features appearing because I'm not limiting the length scale here, because the inner product length scale goes to 0. Okay, so now what I need to do ideally is to combine both worlds. So I will have a fixed length scale in the inner product, and I will have a regularization parameter, and then I see that it converges quadratically, and I have a fixed number of iterations. I have the same for the L-shaped domain, really, and you see the same effect. It's fine. Here you can also use these two scales that I introduced now, just to govern independently how diffuse the interface is and how large the features appearing in the optimal topology are. So of course, this was just a 2D example, but there are other challenges that you have to take into account: constraints on manufacturing, transforming into CAD, robustness with respect to parameters, right? That alpha that was just whatever it was. So in summary, I've demonstrated the simple topology optimization algorithm based on the H1 product, and demonstrated how, if you want to get really the mesh independent number of iterations and the convergence limit, you have to take the regularization the way I did. This is also applied to the specific algorithm of the optimality criteria. So that's it.